We're very happy to have Jonathan Lunine here with us today. He is the David Duncan Professor in the Physical Sciences of Cornell University and the Director of the Cornell Center for Astrophysics and Planetary Science. Can you fit that on a t-shirt? Sorry about that. He does research in astrophysics, planetary science, and astrobiology, and member of the National Academy of Sciences. A recipient of several awards. Now, I presume, and I've seen him give the Steno lectures, he certainly rises to the level of our previous speaker of being able to explain what he does to high school students. So that's a very high honor indeed. But he's also written a couple of books which are very pertinent to the topic of our conference this weekend. Astrobiology, a multidisciplinary approach is one, and the second, Earth, Evolution of a Habitable World. So we're very lucky to have him talk to us today about the scientific search for life beyond Earth, from Mars to the galaxy. He's got a lot of ground to cover. Please join me in welcoming Jonathan.
Well, thank you very much, Chris. In the interest of full disclosure, that's a little out of date. I've been demoted to department chair, so I feel like I'm moving in the direction opposite to Dante's progression in the Divina Commedia, but that's another story. So occasionally I'm asked in an interview or after a talk how my Catholic faith informs my science. And I usually end up answering the question badly with something about better appreciating the glory of the universe and, arrogant answers like that. The real answer to the question is when I'm thoughtful about it, it forces me to be more humble about the science I do. And the search for extraterrestrial life is a scientific endeavor that should promote humility, because just about everything that has been expected in terms of outcomes has really turned out not to be true, especially the nature of those bodies in our solar system where we might go to look for life. It's a very difficult problem because we only have one example of biology, that is life on Earth, which is biochemically all the same. And we only have one planet where that life exists. And so what I want to try to bring across to you today is that some of the discoveries of the last 20 years in planetary exploration have informed us of places where potentially life might exist in our solar system, microbial life, and where we might actually go seek it out. And I'll talk a little bit about how we might do that. I also will talk briefly about how one searches for life in the innumerable planets that orbit the stars of our galaxy. So that's the plan. And let me start with Mars. So I want to begin 55 years ago. Carl Sagan, who was a scientific hero of mine when I was a teenager, in the first book he wrote, which was actually a translation and an expansion of a book by a famous Russian astronomer, Joseph Shklovsky. But Carl Sagan added to that book the following statement. Remember, this is 1966. In assessing evidence for extraterrestrial life, we may be at the mercy of our prejudices. At the present time, there is no unambiguous evidence for even simple varieties of extraterrestrial life, although the situation may change in the coming years. Now, the second half of that statement is still correct today. In fact, even the adjective unambiguous is unnecessary. There is no evidence for even simple varieties of extraterrestrial life. That doesn't mean it doesn't exist, but there's no evidence. And the situation hasn't changed in the 55 years since Sagan wrote those words. The prejudice that he's referring to is this sort of cognitive dissonance between the expectations that planets would, by their nature, be habitable, as Chris Baglow alluded to, over centuries since Galileo, versus the findings, the first findings, in fact, from 2 years before Sagan wrote those words, of the very first spacecraft to fly by and image Mars, Mariner 4, which took a grand total of about 24 images, all of them really noisy, and they all happen to be on the part of Mars that just is the most lunar-like part of Mars. It's not the most typical part, but there it was. And so you see this grainy image from Mariner 4 that really just looks like a picture of the moon. And that created a big emotional reaction among many scientists and also those who fund the planetary program, because suddenly all of these stories about Mars as an environment where civilizations had begun to run out of water and built canals and so on and so forth, that was just wrong. It was like the moon. So that nearly brought planetary exploration to a halt, and to some extent I think it delayed some of the explorations that we are seeing now, delayed those by a couple of decades. So over a period of the next 5 decades, things changed dramatically, especially in the last 20 years. And although we know that the Mars of today is, the surface at least, is uninhabitable, the air pressure is equivalent to the air pressure at 80,000 feet above the surface of the Earth, twice the altitude at which commercial airliners fly. Liquid water is not stable except in a transient way near the equator. And the surface is so chemically reactive from products of photochemistry, ultraviolet-driven chemistry, that organic molecules are sterilized, essentially, when you put them on the surface. Nonetheless, the history of Mars is extremely interesting, and that history has been teased out by increasingly more sophisticated orbiters and now rovers on the surface of Mars. The 3 operating rovers today on the surface of Mars are shown here. 2 from NASA, Curiosity and Perseverance, and if you're close enough, you can probably guess which of those 2 has been on the surface of Mars longer and looks more weathered. And notice the torn wheels, by the way. And then I also have to give a big congratulations to the Chinese Space Agency, CSA, which successfully landed on their first attempt a rover which is also now operating on the surface of Mars, which is really a remarkable achievement. But the Curiosity and Perseverance rovers are very sophisticated. They're nuclear powered. They can operate through the Martian winter. They have very sophisticated experiments. The Zhurong rover is a smaller solar-powered vehicle, but also with interesting instruments on it. Curiosity and Perseverance have landed in places on Mars where there is evidence from orbiting vehicles that standing liquid water was present in the past on Mars's surface. And the story now today about Mars is that with the first 20% of the history of Mars, the first billion years, the environment was very different than it is today. The atmosphere was denser, perhaps periodically, not in steady state. It was warm enough and the air was dense enough for liquid water to exist in standing form on the surface. So the first of those 2 sites is Gale Crater, a large impact crater that was formed about 3.8 billion years ago in the impact of an asteroidal fragment. The curious thing about this crater is it has surrounding its central peak, as you can see in this sort of doctored up image on the left, the central peak, which is typical of an impact crater, is surrounded by and blanketed by this enormous sedimentary set of layers, 5,000 feet thick. How did those form? Well, the measurements of the composition of the surface suggested deposits of sulfur and carbon, carbon compounds that would require liquid water for their deposition. And so the presumption was that the crater got flooded by liquid water soon after it formed. And as that liquid water accumulated sediments from the surroundings, those were deposited. And then as that liquid water was lost over time, as Mars became uninhabitable, wind erosion basically carved the blanket of sediments away so that it has the appearance it has today. And so when Curiosity rover arrived, very early in its mission, it found rocks that you see on the left. And although it's hard to see at this distance, you can probably see that some of those larger rocks have striations in them. And those striations include what's called cross-bedding, which is suggestive of the process of water moving material in the form of sediments and creating these various layers. Essentially, everything that's seen in this scene depicts the interaction of standing liquid water at some point in the past, followed perhaps by the actions of wind. And so this is geologic evidence that the crater was in fact filled with liquid water for some substantial period of time. Add to that that Curiosity's chemical laboratory discovered for the first time on the surface of Mars native organic compounds that were not the result of a primitive meteorite impact or anything like that. These compounds were just under the surface in what are called mudstones. They were dug out and analyzed. They are combined with sulfur, which makes them very, very stable, kind of like the stuff that comes out of skunk glands, which are also organic sulfur compounds. That stabilized them. But they're definitely organic compounds. So there was water and organic carbon-bearing compounds in this region billions of years ago. Now, was there life? We don't know. But the other thing that Curiosity has been tracking are these whiffs of methane in the Martian atmosphere. Methane is very unstable in the atmosphere of Mars. Methane, the simplest organic molecule, was first detected on Mars by an orbiting spacecraft and then from ground-based observations. That methane could potentially be a signature of biology going on in the subsurface layers of Mars, where organisms could survive today, and might be taking carbon dioxide and perhaps hydrogen from water, reacting it to make methane. Or it could be geology. And with the instruments available, it's not possible to tell the difference. The way you tell the difference is to measure the ratio of lighter carbon, carbon-12 with 6 neutrons in it, the ratio of that to carbon-13, which has 7 neutrons. Biology tends through its catalytic effects to incorporate more of the lighter isotope into the organic molecules relative to CO2. Geology kind of does the opposite. Unfortunately, the amount of methane is so small that these instruments can't detect that, and that's going to require a next generation of experiments to see whether this methane is biological or geological. Now, the second rover, Perseverance, landed in this region. This is an orbiting view. This is the western edge of Cicero Crater. It has, as you can see off to the left, a channel which was carved evidently by liquid water, very ancient because you see it's pockmarked by craters. That channel of water breached the crater wall, and sediments flowed out in the form of a delta, which you see toward the left center of the image, very much like deltas that are formed as terrestrial rivers flow out into bays and seas. So there's another place to go to where water was present, it was flowing as a river, it was carrying sediments, and that might be a good place to go look for fossilized microorganisms. So Perseverance landed just to the right of the lobe of that delta. It carried with it a helicopter, Ingenuity. This is an image from the helicopter in its sixth flight, and you can see a variety of rocks that actually also look like mudstones. So there was evidently standing liquid water there as well, although Perseverance has yet to go and analyze those particular rocks. But it will also go drive up to the edge of this delta. The edge is shown there labeled A. That's the closest lobe to the rover. And it doesn't carry the same sophisticated chemical laboratory that Curiosity does, because what Perseverance will do is a more simple chemical analysis, but then it will actually collect these samples, put them in tubes, move those tubes over to a safe landing site, and that material will be picked up by a European Space Agency rover and brought back to Earth by another NASA spacecraft somewhere around 2030. The reason for doing that is that terrestrial laboratory instruments, the ones that we have at universities on the Earth, are much more sensitive and can detect much smaller levels of interesting compounds than devices that you would bring on the rover itself. So this Mars sample return mission is extremely ambitious, and the Perseverance rover is the first step in that. And one possibility is that those samples will contain chemical or physical evidence of microorganisms if they evolved and existed at that site billions of years ago. Let me move on now to the outer solar system. There are three objects where the results of planetary exploration have revealed the presence of subsurface oceans. And in the case of Titan, Saturn's large moon, which you see on the right, there are also surface liquids, standing liquids, of methane and its sister hydrocarbon molecule, ethane. Titan is a cold environment. It's 10 times farther from the sun than we are, but it has a dense atmosphere. The air is 4 times denser than on the surface of Titan than it is at sea level on Earth. It's nitrogen and methane, so ultraviolet radiation at the top of the atmosphere produces a variety of organic compounds. They sediment to the surface and end up in these methane lakes and seas. Could there be a kind of exotic chemical evolution that would lead ultimately to a kind of life completely biochemically different from the Earth? That's a speculation. I'm not going to talk further about Titan for want of time, but it's the best place to learn how different biochemistry could be from one world to another. The other two objects, Europa and Enceladus, have liquid water oceans that might perhaps support life. So Europa is the second of the Galilean moons of Jupiter. It's the size of the Earth's moon. Its surface is ice-covered, but the bulk of this satellite is actually made of rock. We know that from the density that's measured by determining the mass by flying spacecraft by it. And what's curious about it is it has very few impact craters, but it has a very intriguing geology, which you see from an image from the Galileo orbiter. And you can probably guess by staring at this that if you were to cut these blocks up, the ones that have the fractures in them, using Photoshop, and move them back together, that they would actually all fit. And indeed they do. That was work done by a graduate student at the University of Arizona, Randy Tufts, in the 1990s. So evidently this ice crust has been broken up and moved around, which says maybe there's a liquid layer of water under the surface. And in fact, Galileo discovered that water ocean, and it did it with an instrument called a magnetometer, which measures magnetic fields. So Jupiter has a powerful magnetic field, 20,000 times stronger at the cloud tops of Jupiter than our Earth's magnetic field is at the surface. And like the Earth's magnetic field, the axis of rotation of Jupiter's magnetic field is tilted relative to its rotation axis. So if you're standing on a moon orbiting at the equator of Jupiter, which Europa is doing, looking at that magnetic field, you see it swaying back and forth due to the rotation of Jupiter, which means that at your position, that magnetic field is time varying. Now, if you're as boring as a tennis ball, something that doesn't conduct electricity, nothing will happen. But if you're a human being or an object that's full of water, salty water, that time-varying magnetic field will generate what are called eddy currents inside your salty water, and those eddy currents in turn will generate a secondary magnetic field, what's called an induced field. And that is exactly what the Galileo magnetometer measured on multiple flybys of Europa in the late 1990s. And the geometry of that induced field and its strength says that the conductor that is causing this is not a tiny iron core in the center of Europa. It is, in fact, a liquid water ocean that's very, very close to the surface. How close? Well, some parts of Europa have these curious fractures and ridges, as you see on the top. which would argue that the crust is very, very thin. And Europa, which is in an orbit of Jupiter that's not a circle but an ellipse, experiences a variable tidal force from Jupiter. So it's squeezed and pulled by the gravity of Jupiter, and that opens these fractures, and the circular nature of those fractures suggests a crust that's less than a kilometer thick. On the other hand, the image on the bottom is of one of the few impact craters on Europa, called Powell. It's about 30 kilometers across. The fact that you can still see the topography in the ice from the impact says that that part of the crust is very thick, possibly twice as thick as the diameter of the crater itself. So as in the depiction on the lower right, Europa's crust may be variable in thickness, and one would like to know where it is the thinnest, where one might go to actually sample the ocean. Because we know very little else about this liquid water ocean except that it exists and except that it appears to have salt in it. There are intriguing places on Europa where there are interesting colorations and signatures in the light coming back from Europa, signatures that are split up into component wavelengths in a technique called spectroscopy, which suggests the presence of salts. The most spectacular of those indicators actually came from Hubble Space Telescope spectra, collected and analyzed by a group at Caltech. Samantha Trumbo led that group as a graduate student. She's now completed her Ph.D. And the distribution of intensity of light versus wavelength indicates that there is sodium chloride on the surface of Europa, and that it's concentrated in areas that correspond to those weird chaos terrains, which are marked out with the black outlines in the lower left. So the fact that it's sodium chloride says that it's probably not something from a neighboring moon like Io, which doesn't really have much chlorine as far as anyone can tell. And the fact that it's concentrated in the very terrains that seem to be the thinnest and seem to have been fractured and moved around suggests that it's coming out of an ocean, that it is native salty material that's being deposited on the surface. And that in turn says we could go to Europa, land in the right place, and sample the ocean to see whether there's evidence of microorganisms. But these Earth-based images don't give us a precise enough result. And so NASA has a new mission to Europa, Europa Clipper, which is going to be launched in 2024. It will not orbit Europa because it's too deep in the radiation field. Clipper will do an eccentric orbit around Jupiter itself and make several dozen flybys of Europa with a very sophisticated instrument package that includes, in red, two instruments called mass spectrometers, and these actually take in atoms and molecules. They ionize them, electrically charge them, and through an electric field or a magnetic field in the instrument itself, usually an electric field, their path is bent, and the extent of bending tells you the mass of the molecule or the atom. So you can identify this material. So mass specs and SUDA will do that analysis of material that's on the surface or being extruded perhaps in geysers. The other instruments in white are remote sensing instruments from the ultraviolet to the infrared. Reason is a radar that will penetrate to determine the thickness of the crust, and then there will be a much more accurate magnetometer that will be able to tell us more precisely the salinity of this ocean. And one important question is whether there are carbon-bearing molecules in the ocean of Europa, because that's necessary for life. So the MISE instrument, M-I-S-E, which I'm involved in as co-investigator, will be able to tell us that and tell us specifically where on the surface those organic molecules have been deposited. And that then would indicate whether it is worth sending a lander and where you would send the lander to sample that material and see if there are biological molecules. Because organic just simply means containing carbon. It doesn't mean biological. So that's the next step for Europa. I want to move on to Enceladus. This is a much smaller moon. It's a moon of Saturn. It has a volume about 500 times smaller than that of Europa, but it's geologically active. It has a series of jets at the South Pole that merge to form a large plume of gas and dust and ice that pours out into orbit around Saturn. Because Enceladus has that plume, it's possible to directly sample the source of that material by simply flying through it. And the spacecraft that did that was the Cassini-Huygens mission, which was one of the most ambitious planetary missions ever conceived of. It spent 13 years in orbit around Saturn. It deployed that saucer, the gold saucer-shaped Huygens probe, you can see on the left, to land on the surface of Titan. That's another talk. And it made many, many discoveries during its 13 years around Saturn, one of which was that Enceladus has this active plume. So the south polar region that you see in the upper left image is crisscrossed by long fractures that are hundreds of miles in length. If you look at Enceladus from the night side, so that the sunlight is being scattered by material as it comes toward you, there's very evidently a plume of material. You're seeing the dust and the ice. That's another Cassini image. That's on the top center. And then top right, that material goes into Saturn orbit because the gravity of Enceladus is quite low. It's 100 times weaker than the gravity on Earth. So all this stuff goes into orbit, or most of it does. Then on the lower left, you see a higher resolution image taken by Cassini, which demonstrates that that plume of gas and ice is at its source a series of jets, perhaps as many as 100 jets, that are coming out of these fractures. And then in the very highest resolution image, which was difficult to get because of the smearing effects of the speed of the spacecraft as it flew across Enceladus, you see on a scale of tens of meters, very, very intricate fractures and peaks and pinnacles where material is evidently coming out and being deposited. And so this is the source region. But where is this material coming from? Is it just warm ice or is it liquid? There were a number of observations that Cassini also made with various instruments that demonstrate that the source of this plume of gas and ice and dust is a subterranean ocean, a subsurface ocean. So the first two bullets here describe two observations that Cassini made. One, by flying past Enceladus repeatedly, the velocity changes of the spacecraft could be measured. Those velocity changes were due to the mass distribution inside of Enceladus, because the mass creates the gravitational force that determines the trajectory of the spacecraft. And the mass distribution there indicates that while Enceladus is about half rock and half water, it can't all be water ice, that at the south polar region there is a lens, at least a lens, of slightly denser material sandwiched between the ice on top and the rock toward the center, the rock on the inside. So that slightly denser lens arguably is liquid water. And in fact, the second observation, the second bullet here, labeled imaging, is a set of observations made over many years where the rocking motion or the libration of Enceladus was measured by Cassini. Now, our own Earth's moon librates. If you were to take images of it over a complete monthly cycle, you would see that the same face doesn't quite point toward the Earth. It rocks back and forth because the moon's in an eccentric or elliptical orbit. And so the orbital speed of the moon changes as it goes around the Earth, whereas the spin of the moon stays the same, and so the spin lags or leads relative to the orbital velocity. And that creates a force or a torque which further enhances that rocking or libration motion. Same thing with Enceladus around Saturn. You can calculate how high an amplitude, what the amplitude of that rocking motion should be if Enceladus were simply a solid ball of rock or ice or whatever. And it turns out that the actual libration amplitude, the actual amount of rocking, is 3 times larger than that number, which suggests that somehow Saturn is pulling on just a portion of Enceladus, which would be the outer portion, and that outer portion is sliding on top of the bulk of the object. So a small portion of the mass is being tidally pulled separately by Saturn. So having an ice crust sliding back and forth across a relatively frictionless or low friction layer is, in its simplest form, telling us that there is a liquid water ocean underneath the ice crust and above the silicate core, the rocky core of Enceladus. But is it water? The answer is yes. Most of the grains pouring out of Enceladus are water ice, and the largest of those grains, the micron-sized grains, contain salt. Cassini has on it 2 mass spectrometers, those instruments that measure the composition by collecting material and ionizing it. And as Cassini flew through the plume of Enceladus that it had discovered, it flew through that plume 12 times, the mass spectrometers for gas and for dust collected material. And the ice grains that were collected were broken apart as the spacecraft flew at high speed, and the molecules were analyzed. And those ice grains contained, on average, about 1% salt, which is pretty salty. The Earth's ocean is about 4%. Now, ice itself, water ice, doesn't dissolve salt very effectively. Salt is not very soluble in water ice. And so that 1% salt, it's actually as much as 2% in some grains, tells us that those ice grains were originally liquid, that they were liquid water where the salt was dissolved in at a level of 1 to 2%. Then as that material was ejected into space, it flash froze and the salt was trapped in the ice. So that, described in the 3rd bullet, is evidence that this low viscosity layer, this liquid layer, is salty water. And the final piece of evidence is that while the overall surface of Enceladus is very, very cold, 10 times farther from the sun than the Earth is, very bright and reflective with its water ice surface, that surface temperature is 75 Kelvin, 75 degrees above absolute zero. But at the fractures, those south polar fractures, Cassini measured temperatures of upwards of 200 Kelvin. And that's at the surface of the fracture. If you extrapolate those temperatures down through those cracks, you find that you don't have to go very far, maybe a few kilometers, before you get to the melting point of water ice. So put all that together, there's an ocean. But more interesting than that, even, is that at the base of that ocean, which is presumably the rocky silicates that provide the high density of Enceladus that's been measured, there is chemistry going on with the water. One of those 2 mass spectrometers also measured very tiny grains that are a billionth of a meter in size, nanometers in size, part of the population of material coming out of the plume into Saturn orbit. Those tiny grains, we'll call them nanograins, contain almost pure silicon dioxide. And so this is a graph from a paper published which shows the mass spectrum. It's not given in mass units on the horizontal scale because this kind of mass spectrometer is called a time-of-flight mass spectrometer. It measures in the instrument the time it takes for those ions to travel from one charge plate to another, and that tells you the mass. But the species that are identified from the time of flight, and therefore the mass, are shown there. And notice that silicon, S, and oxygen, O, are in a ratio of 1 to 2, which is silicon dioxide, SiO2. In larger crystalline form, that's quartz. These are too tiny to be crystalline quartz. But where does that stuff come from? It comes from the rock. How does it get there? Well, one plausible way is that water, you see the chemical reaction at the bottom, water reacts with a common mineral called phthalate. It's an olivine-type mineral, which contains iron and silicon and oxygen. And the water reacts with that to make magnetite, another very common mineral, plus the leftover silicon and oxygen, SiO2, 3 of those, and some leftover hydrogen from the water. For that reaction to go, you need hot water, 50 Celsius at least, so 320, 330 Kelvin. And so evidently there's hot water there. It's water circulating through the rock itself, which is heated by tides and maybe by radioactivity. And then as the aqueous silica is formed, it's dissolved into the water. As that water moves back up into the ocean, which is colder, that material precipitates out in the form of what's called a colloidal suspension, and then evidently ejected out of that ocean before those particles have time to agglomerate into larger particles. Now, does this story make sense? Well, it would make sense if Cassini detected the hydrogen as well. Hydrogen's hard to detect because as the spacecraft is shooting through the plume, it's colliding with water molecules from the gas and ice grains, and that process itself breaks the water apart and makes hydrogen. That's not the hydrogen we're interested in. That's produced by the spacecraft. So it's possible to tune one of those instruments, the gas mass spectrometer, to detect native hydrogen coming in a certain direction and also to minimize the effect of those collisions. I can describe that to you in the coffee break. And lo and behold, in that last flyby with the instrument tuned to that configuration, the INMS mass spectrometer discovered hydrogen, 1% relative to water, quite a lot. And it's even possible to spatially locate it as being in the region of the fractures. So this reaction seems to be what's going on, and what that means is that underneath the ice there is an ocean, and underneath the ocean there is the silicate, and there are reactions going on between the rocky core and the water, which is just what happens at hydrothermal systems on the Earth where primitive microbes exist, where they feast on hydrogen. Hydrogen is the restaurant at the bottom of the ocean for simple microbes. But are there organic molecules in this ocean? And the answer for Enceladus, we actually know, as opposed to Europa. The answer is yes. So Cassini also detected, in addition to water and hydrogen and ammonia, methane and ethane and carbon dioxide in fairly high abundances. But even more interesting is that it detected much heavier organics. So on the right is a figure from a paper from the dust mass spectrometer showing various peaks in the mass spectrum. Those numbers are the atomic mass or molecular mass identified from the time of flight. And those peaks that you see labeled by HMOC are separated in mass by 12 or 13, which corresponds to carbon by itself or carbon and hydrogen. So evidently, this is a series of high molecular weight organic carbon molecules. This instrument doesn't have the resolution to tell us what molecules they are specifically, but it can tell us that they're organic molecules. So in the Enceladus Ocean, there is salty water, there are organics, and there's a hydrothermal chemistry going on. And so does this ocean have life? It sounds like it's habitable, but is it inhabited? Question that Cassini couldn't answer with its instruments. So one simple way to address that is just to go back to Enceladus and do the same thing that Cassini did. Fly through the plume, but this time fly through it with more advanced instrumentation. One relatively low-cost way to do that is one that I proposed with a group of other scientists and NASA's Jet Propulsion Laboratory called Enceladus Life Finder. And yes, it's solar-powered. Cassini was nuclear-powered. And the goal of this mission is twofold. Number one, to do a detailed assay of the habitability of the ocean. What I've told you is that the ocean in a basic general sense is habitable. But are there phosphorus and sulfur present? Phosphorus is necessary for life as we know it. The phosphate bond is the energy storing bond of life. What is the acidity of the ocean? Cassini gave us a preliminary answer to that with a large error bar. What are the temperatures of the hydrothermal system? You can measure that from the plume by measuring certain pairs of ions. And then what is the extent of the hydrothermal chemistry? And then on the right side, search for biosignatures. Measure the sources, the reactants, and the products of common metabolic processes like methanogenesis, carbon dioxide plus hydrogen making methane, and other more complex metabolisms. So ELF would do that. Determine the abundance pattern of common biologically useful molecules like amino acids and fatty acids, which form membranes. Those things are formed in nature in the absence of life, but the particular pattern of abundances of certain amino acids, glycines versus lysine and aspartic acid and so forth, it's a very different pattern in biological systems than it is in abiotic systems. In abiotic systems, as you might expect, the most abundant amino acid that you form is the easiest one to form, but is the least useful in producing biological structures. Same with fatty acids. And then finally, measure those C12, C13 ratios to determine if carbon is being processed through biological systems and capturing preferentially the light carbon. Now, the way we were going to do this with ELF was just to use mass spectrometry, this tried and true technique, but to have a mass spectrometer with a higher mass resolution. So the Cassini mass spectrometers, exemplified by the little graph on the left, were only good enough to tell you whether something had a mass of 27 or 28 or 29, basically an integer number of neutrons and protons. So a mass of 28 could be carbon monoxide or N2 or a hydrocarbon. Can't tell the difference. But in fact, molecules like CO and N2 actually don't have exact masses of 28. The binding energy of their nuclei correspond to a slight increase or decrease of mass relative to that integer number. And high-resolution mass spectrometers can measure that, as you can see on the right in a laboratory spectrum. And those mass spectrometers are being flown to Europa. So if we fly them to Enceladus, we would clean up on this. So far, NASA has not been convinced to fly this, but we're going to try again. An alternative approach, which a number of us have also looked at, is spend more money. Can't convince NASA to spend a little money, convince them to spend a lot of money. And so a so-called flagship mission, several times more ambitious, could land on Enceladus and collect a lot more material than you actually get from flying through the plume. And with that larger amount of material, it would actually be possible potentially to capture cells that have been blown out of the ocean through these jets, and maybe even to do some genetic analysis to amplify information-carrying molecules and determine their coding. So that would be a much more ambitious approach, and we'll see which of these. I think one of these will eventually go. Time will tell. So let me finish in the last 4 minutes that I have with the galaxy. There are known almost 5,000 planets orbiting around stars other than the Sun. And that's in our galactic neighborhood, as exemplified by that orange shape there, which shows you roughly where those objects are on a planar map of the Milky Way galaxy. Which, by the way, says on a statistical basis, on average, every star has a planet. Planets are as common in our galaxy, and presumably the universe, as stars are. So many of those would be at the right distance from their parent star to have liquid water. They would be in the so-called habitable zone. But we can't go across the interstellar vastness of space with spacecraft and analyze them, at least not in the lifetime of anyone in this room, even the youngest people in this room, guaranteed. So what do? Well, we take spectra. We look at the light coming from these planets, break it into its component wavelengths, and look for telltale signatures of molecules. But the problem there, as Giordano Bruno first pointed out in 1600, before he was invited to a barbecue, was that these planets are lost in the glare of their parent stars. And so you need to look at special orbital configurations or use very, very large telescopes. He didn't think of that part, of course. Or use very, very large telescopes to pull the light of the planet out from the light of the parent star. a very tough problem. And what do you look for? The problem with looking for molecular signatures in an atmosphere is that they could be caused by life or could be caused by something else. For example, photosynthesis. Water and carbon dioxide with sunlight combined in a cell makes molecular oxygen and carbohydrates. So look for molecular oxygen in the atmosphere. Or look for the products of molecular oxygen, ozone, which is even easier to see in spectra. The problem with that is that molecular oxygen and ozone are also formed by non-biological processes, by photochemistry. So what do you do then? Well, take the next more difficult step. Look for actual chlorophyll on the surface of a body or a similar kind of pigment. Chlorophyll has, as you see in the middle panel, a very distinct red edge where it stops absorbing sunlight. Look for that red edge in the spectra. Much more difficult than looking for oxygen, but possible. Well, maybe it's just some, weird green geological thing. So what do you do then? Well, look for the atmosphere actually breathing, which is on the right, and that's the toughest thing to do. So on our Earth, we have seasons, and also most of our land mass is concentrated in the northern hemisphere, and that's where the land plants are, of course. And so there is a seasonal and annual variation in the amount of leaf material that takes up carbon dioxide. I'm going to turn my timer off. That takes up carbon dioxide. And so on an annual basis, in the summer, the CO2 abundance goes down, northern hemisphere summer, and northern hemisphere winter, it goes up. Southern hemisphere is mostly ocean and Antarctica, so the effect there is much less. So that leads to this oscillation in what we call the Keeling Curve. Now, if there's a planet around another star with seasons and the continents happen to be distributed asymmetrically, there should be a variation in the Keeling Curve like that. But this is really difficult to detect because it requires detecting a change in the total amount of CO2 of just a few parts per thousand in the case of the Earth. So how would all this be done? With giant space telescopes. The first of those, the James Webb Space Telescope, will be launched later this year. It is an extremely sensitive infrared telescope with a mirror 2.5 times larger than Hubble, so large that it has to be folded up, as you can see here, to fit in a spacecraft, and so sensitive that it can tease the light of a planet out from that of its parent star in the optical and the infrared. But that requires sending it well away from the Earth, which has a strong heat signature. In fact, it will be placed 1 million kilometers from the Earth, beyond the Earth-Moon system, and shielded by that very complex sun shield that you see there. This is the most ambitious space telescope that has ever been built. I hope it works. During the commissioning phase, I plan to be on tranquilizers because it is really complicated. Actually, we're being recorded. I don't really mean that. I will weather through it. All right, so I want to close with what if we succeed? What if we actually find life? So I want to make 2 points about this. The first is a point that Carl Sagan made, this time in the last book, a book that was published the year of his death. One has to be very careful in the search for life not to convince oneself of false positives. And I won't read this quote, you can read it yourselves, but in the history of planetary exploration, we have already fooled ourselves twice. Once with Viking, where a supposed positive signature of life turned out to be only reactive chemistry in the Martian surface, in the Martian soil, and the other with the Martian meteorite ALH 84001, where these sort of weird images in an electron microscope image looked like tiny worms, and they were not tiny worms. They were epitaxial growth in the surface material. We have a talent for deceiving ourselves, as Sagan said. Skepticism must be a component of the explorer's toolkit, or we will lose our way. And this, I think, frankly, gives Catholic scientists an advantage because we stand in the face of this enormity of God's creation, and it only makes one feel humble and small. And that feeling, I believe, contributes more to the ability to remain skeptical and remain detached than if we did not have that view. And in that regard, I then want to close now with the words of Thomas Aquinas. If we do, in fact, find microbial life elsewhere, what does that tell us about life on Earth? Does that make us less special? And the answer, self-evidently, is of course not. And Aquinas wrote in his theological compendium about the multiplicity of creatures and organisms, that this multiplicity was devised by the divine intellect and established so that the divine goodness might be represented by created things in various ways, and that different things might participate in the divine goodness in varying degree. All this was so that a certain beauty might shine forth from the very order existing among diverse things, a beauty which would direct the mind to the divine wisdom. Extraterrestrial life, exotic biochemistries are part of that order that is part of the evolution of the universe that comes from the divine wisdom. And to find that is only to have an even deeper appreciation for the enormity, in fact, the infinite nature of that divine wisdom. Thank you.
Well, thank you very much, Jonathan, for that perspective. I would like to have some questions now. I'm sure there are many.
So I'd like to ask, you said, what if we succeed? And my question would be, what if we don't?
Yeah.
Because you've already pointed out two cases. I would also throw in the whole belief that there was intelligent life on Mars from the early part of the 20th century. And as you already mentioned, the history of this idea is not real good. We always think that the universe is going to look more like us than it really does. So what if we don't? And how far will we have to go before you would say, oh, geez, this isn't working?
Right. Well, so that presumption that other places must be like Earth is a sort of an intellectual conceit that, somehow, the Earth is it, as opposed to the kind of grandeur that one sees in the variety and multiplicity of things, which Aquinas talked about. So, for example, when it was observed that Mars would darken at certain seasons of the year, the assumption was, oh, it's vegetation. It's just like the Earth. It isn't. Mars has dust storms, and that's what darkens and lightens Mars. So everything that has been learned from planetary exploration boils down to planets and moons, for that matter, are really different from each other, that small differences in starting conditions lead to a lot of variety. And so that means we have to be very careful in our preconceptions. If it turns out that the ocean of Europa is habitable but has nothing in it, if it turns out that the ocean of Enceladus is habitable but has nothing in it, habitable but not inhabited, then we have to look at a couple of different possibilities. One is that the beginnings of life, that chemistry, requires being on a surface with ultraviolet radiation, and it can't happen at the bottom of an ocean. And in fact, some biologists have argued that, that in fact, life on the Earth didn't begin in the depths of the ocean, it began on the surface and ended up in the ocean. Because those two places don't have surfaces where that can happen or could have happened, then that's a way out if you don't find life. That it still is a natural outcome of chemical evolution to have life, but those conditions aren't right on Enceladus or Europa. Now, what about Mars? I mean, early Mars had an atmosphere, had standing bodies of liquid water for a long period of time. So in that case, those surface conditions would have been, in fact, fulfilled. So what if we come up empty with Mars, after decades and decades of trying? Then maybe the answer is that, the origin of life involves an incredibly narrow bottleneck that chemistry is just unable to cross for whatever reason. It doesn't say that God had to violate his own natural laws to make life, but it would just say that it's an extraordinarily rare occurrence, but rare in the sense that out of 4 or 5 potentially habitable worlds in our solar system, only one of them got it. To me, that makes for a narrow but not super narrow bottleneck. So that's what it tells me. It doesn't really tell me anything theological. because, you know, getting a negative result for planets around other stars, it's going to be much more difficult to determine the significance of those negative results and whether in those cases it really means there isn't life. So now, if you said, what if you absolutely knew there was no other life in the galaxy, that we were alone in the galaxy, I'd have to stop and think about that. But I don't think that's what's going to happen.
I'm Bob Novak from Iona College.
Yes, hi, Bob.
Back in 2009, we published a paper. I worked with Mike Mumma from the Goddard Space Flight Center.
Yes.
And we identified methane on Mars.
Yes.
Now, since then, or since 2003, we've been looking for other organic molecules. And to date, at best that we have gotten are upper limits. So some of the things that we're looking for instance, we're looking for the presence of ethane. We're also looking for carbon-13 methane. Mm-hmm. And up to now, those regions, the spectra have been below the noise level. Yeah. So we have recent data that we took 2 months ago, and hopefully we'll find something when it gets analyzed.
Yes.
But what we have found is the presence of methane is fairly localized, and it's also seasonal. In fact, the concentration of methane likewise varies from sunrise to midday to sunset.
Right, that's right. And, you know, that was, the Curiosity rover measurements indicated that kind of diurnal activity, but the Earth-based measurements that I referred to were, in fact, your measurements. It was the Mumma et al. Data, which were criticized by some groups as being artifacts, but turn out to be right. It turns out to be methane is really there. So, you know, congratulations to your group for a very, very difficult observation. You know, boy, teasing out C13 versus C12, that's a tough thing to do.
Let me make a proposal, Steve, that we continue this discussion. If somebody needs the break, we were supposed to take a few minutes ago, go ahead and take the break. But we'll plan on starting Karen's talk in 10 minutes.
Right,
but I think there's so much discussion here, we should keep it going.
There is no break between Jonathan's talk and Karen's. So I think we actually have 3 minutes more for questions.
Okay.
Yeah,
Okay.
but the schedule was modified.
I'll talk fast.
So there was a recent claim of, I think it's phosphine in the atmosphere of Venus. I know Venus isn't one of your main planets, but is that still a live controversy, or was it refuted?
Yeah, so phosphine is pH 3. Phosphorus comes out of volcanoes, and Venus is volcanically active, so it's a plausible constituent. But that observation that Robert Shearer referred to has been questioned by other observers. It was a measurement made with a couple of different radio telescopes. And there's a big debate about whether, in fact, it's really there or not. There's also a tentative detection of phosphorus compounds from the Pioneer Venus mass spectrometer from 1978. So actually, a graduate student of mine and I wrote a paper about pH 3 in which we argued that contrary to the kind of nominal view that pH 3 is actually a bioindicator, because it's very hard to make reduced phosphorus in that environment, that you could actually make it from what are called phosphides that would be present in lavas, and there is evidence that Venus is volcanically active. So is it really there? It's very hard to know. This new Discovery mission that NASA just selected will give us the answer when it arrives with its better mass spectrometers, but it doesn't have to be a biosignature. It can be a volcanic signature.
Great talk, Jonathan. I just had a question about Mars, water. So you showed all this evidence that there was all this liquid water on the surface of Mars, and so what happened to it? Yeah. And is it liquid under the surface, like these moons?
So there is still water at the surface. It's buried in the ice caps. There's some places where there may be water fairly close to the surface as well, buried in the soil, but the depth at which water exists in either bound form or ice, gets deeper and deeper down below the surface as you go to the equator. So, and that's been mapped by long wavelength radars. What happened to all that water that was at the surface is, the $64,000 billion question. So for a long time it was thought that it was just eroded away by impacts, that because Mars is small, impacts eroded the atmosphere, and away went the CO2, the greenhouse gas, and the water went with it. But a more recent paper, which is based on the rover studies and orbiter studies from Bethany Ehlman at Caltech, gives a very interesting story where water actually ends up in the subsurface of Mars, that as time goes on, it's lost to chemical reactions and gets bound with minerals, hydration. And so most of it is actually still there, but it's just in the ground and can't get out in this very cold environment.
Great. Well, thank you very much, Jonathan. Let's thank him.